Hello and welcome to our presentation. We will talk about the last chapter in the Calculus 1B class, and that is the differential equation. We divide the chapter into 4 parts, so let's begin.
The first method that we learned in chapter 9 is the separation method. A separable equation comes in the form of fy dy dx equals to gx. Then you take the dx to the other side and you integrate both sides. By doing so, we are able to solve a separable equation. In example 1, you have x squared y bar equals to y minus xy. X squared dy dx equals to y bracket 1 minus x. By dividing both sides by x squared and y, you'll get this form. And when you integrate both of them, you'll get ln of y equals to integration of 1 over x squared minus 1 over x dx. By integrating this, you'll get ln y equals to negative 1 over x minus ln x plus c. To get y, you simply just move ln to the other side and you get e to the power of negative 1 over x minus ln x plus c. In the second example, we have y dy equals to 4x bracket y squared plus 1 dx. Then you divide both sides by y squared plus 1. To continue, you just integrate both sides and you'll get it in this form. You will then have to square both sides and move the one to the other side to get y squared, and you just simply square root both sides to get the answer. So the second thing we learned in chapter 9 is first order linear equation. Firstly, we start from the differential equation, and then we multiply mu x in both sides. The equation will look something like this. By using product rule, we know that d over dx of mu xy is equal to differential of mu x y plus mu x differential y. We then add differential mu xy into the equation, then minus it again, so it will be null. And the equation will look something like this. We continue to simplify the equation and combine the equation using the product rule and continue to the other part of the equation. And then we let differential of mu x minus px mu x equal to 0. And you move part of the equation to the right side. By separating the mu x with the px and completing the rest of the function, the final form of the function should be mu x equals to e to the power of integral px dx. Back to the function, differential of mu x y equals to mu x fx. To change the differential of mu xy, we integrate the other side to get rid of the differential. Move mu x to the other side to have the function of y. Here's the first example. You have x squared times y bar, which is equals to y minus x, y. We first take the y outside. Then we move all of the function to the left. We times all of the function with x squared to get rid of the differential y function on the most left.
We know that px equals to x plus 1 over x squared.
So mu x is e to the power of integral x minus 1 over x squared. The mu x will be x e to the power of 1 over x, simply by simplifying the equation. By multiplying mu x both sides will change the function to differential of x e to the power of 1 over xy equals to 0. Integrate the right side of the function. From the question we know that y minus 1 equals to negative 1. We use this information to reveal the c function. From this we know that c is 1 over e. So the final form of the y function is 1 over x e to the power of 1 plus 1 over x. For the second example, we have y bar plus 2y equals to e minus t. This function already reveals the px, and that is 2. So the mu x equals to e to the power of integral 2 dt. The mu x will be e to the power of 2t. The differential of e to the power of 2ty equals to e to the power of minus t times e to the power of 2t. We integrate right side to get rid of the differential. The function would be e to the power of 2t equals to e to the power of t plus c. We move e to the power of 2t equals to e to the power of t plus c over e to the power of 2t. So we have y equals to the e to the power of minus c plus c e to the power of minus 2t. We know that y0 equals to 0. We insert this information to the function. We found that c equals to minus 1. So the final y function is this. After learning about the way we solve a linear equation, let's try to solve a slightly different form. It is called Bernoulli equation. This method is found by Leibniz in 1696. So when do we use Bernoulli? We use Bernoulli when we have this kind of form. The difference is that we have the y to the power of n on the right side of the equation. The first step in calculation equation is to isolate the y prime. By doing so, we get the standard form, which pretty much looks like a linear equation. Then we let u equals to y to the power of 1 minus n. Calculate the du over dx. After deciding the u and getting the du over dx, we can start substituting it into the equation, making the equation in the form of u and x only. By doing so, we will have a linear equation. Then we have to isolate the du over dx again by dividing both sides by whatever attached to it. After making it into a standard linear form, we can determine what the px is, and then we just have to do the same steps as the linear equation. Here's the first example of how we can use Bernoulli. Remember, the first step we have to isolate the y prime, so divide both sides with x. Then we have to divide the right side by y to the power of n, which is y squared in this question. Now we can let u equals to y to the power of n minus 1. So u is 1 over y. Remember to also calculate the du over dx. Substitute the u and du over dx to the equation, making everything in terms of u and x. Now we have a linear equation. Multiply both sides by -1 to make the du over dx positive. After making it into a standard linear form, we just use the method we used to solve linear equation. We can find out what the px is, and then we can also calculate mu x. Now we calculate the integration of dx e to the power of x times u equals to integration of negative x e to the power of x dx. After finishing the integration, we put u on the left side and then substitute it back into y. Here is a second example. Remember, the first step is to isolate the y prime, so we divide both sides by xy squared. Now we have isolated the dy over dx. The next step is to multiply the right side by y squared. Now we can let u as y cubed and calculate du over dx. We just have to substitute it into the equation, making everything in terms of u and x. Now it's a linear equation. To isolate the du over dx, we multiply it by 3 on both sides. Given that we have the standard form now, we can decide the px, which is equals to -3 over x. After integrating px, we can get the mu x as 1 over x cubed. Now we just have to find out what is mu x, which is 1 over x cubed. After integrating both sides, let's put u on the left side of the equation and substitute it back into y. Given that the information that y1 equals to 2, we can calculate c, which is 8. By putting back the c into the equation, and now we have the final equation, which is cube root of -3 ln x plus 8x cubed. So the next thing we learn in chapter 9 is the substitution method. For the first step, take a term of the equation and replace it with a variable u. The key is that the new variable have to cover all instances of the variable y. Second, solve for dy dx regarding to u and du dx and take its derivative. Third, plug in du over dx and solve for u. Last, plug u into the original term replaced and solve. Let's follow the procedure with easy equation. dy over dx equals to x plus y plus a squared. So first of all, I let u equals to x plus y plus a and take its derivative. Du over dx equals to 1 plus dy dx. Next, I solve it for dy dx. So, dy dx equals to du over dx minus 1. Next, I plug u and du dx into dy dx equals to x plus y plus a squared. Then the equation turns to du over dx minus 1 equals to u squared. Solve it for du dx. Du dx equals to u squared plus 1. Now it's separable. So we just take dx equals to du over u squared plus 1 and integrate it. This will give us x plus c equals to tangent inverse u. We then solve for u. U equals to tangent x plus c. For the last step, I plug the original term, which is u equals to y plus x plus a. So you will get y plus x plus a equals to tangent bracket x plus c, which will give us what y is. So we have the first example, which is dy dx equals to tangent square x plus y. At first, we let u equals to x plus y, and du over dx equals 1 plus dy dx. Solve it for dy dx, and we will get dy dx equals to du over dx minus 1. So, dy over dx equals to tangent square x plus y turns to du over dx minus 1 equals to tangent square u. Du over dx equals to tangent square u plus 1, which is secant square u. Then, du over dx equals to secant square u, which will then give us dx equals to du over secant square u, which in turn gives us cosine square u. By integrating both sides, we will get x plus c equals to 1 over u minus 1 over 4 sine 2u. By plugging in u equals to x plus y, we will get it in this form. So for the second example, we have y dx plus x bracket ln x minus ln y minus 1 bracket dy equals to 0. First, I need to make dx over dy. So we start with dividing by y dx. So we'll get it in this form. Following a low logarithm, we'll get 1 plus x over y bracket ln yx over y minus 1 bracket dy dx equals to 0. We then times everything by dx over dy. Now by getting this form, we can replace it. So we let u equals to x over y, which gives us x equals to uy. Take that derivative. Dx over dy equals to u plus y du over dx. So we plug it in. So u plus y du over dy plus u ln u minus u equals to 0. U is then cancelled, so y du over dy plus u ln u equals to 0. We then take u ln u to the other side, making it negative. By doing so, we can just divide by y and u ln u, which gives us du over u ln u equals to negative dy over y. By integrating both sides and using u substitution, we'll then get du over u ln u equals to ln bracket ln u. So the ln of ln u will be equals to negative ln y plus c. By taking ln out from both sides, y equals to negative ln u plus c. And when we substitute back the original term, we will get what y is. So we go on to the next part of the chapter, which is different applications. And we'll first start off with Newton's law of cooling and heating. The base theory of this problem is by differentiating temperature in respect of time, which is equal to K times T minus T0. This calculation will give us the formula of Newton's law of cooling. So we begin by swapping T minus T0 with dt. We then proceed to integrating both sides to get ln T minus T0 equals to Kt plus C. T minus T0, which will then equals to A e to the power of Kt. T of T will be T0 plus A e to the power of Kt. This is Newton's general law of cooling and heating. If we draw the graph, we can see that the value of K is always negative. The difference is in the value of A, for which A is positive for the cooling process. In contrary, the value of A will be negative when the heating process occurs, while K remains negative. In the first example, we have a condition of a thermometer from an inside room to an outside room where the temperature is 5 degrees Fahrenheit. So when T equals to 0, temperature is X. When T equals to 1, temperature is 55. When time equals to 5, temperature is 30. And when time is approaching infinity, temperature is 5. And we write the general equation. So when we put that time is approaching infinity, the temperature will become 5 plus A times 1 over e to the power of infinity, which will give us 5, A plus 5. Next, we put the rest of the information that we are given into the problem. When the time is 1 minute, the temperature will be 55 degrees. Then when the time is 5 minutes, the temperature will be 30 degrees. We put all those information to the general equation. After that, we'll do some calculation by dividing the lower temperature to the higher temperature. This calculation will give a value of the e to the power of k. Then we go back to the general equation when the time is 1 minute and put in the value of e to the power of k. We will solve the equation and find the value of a, which is roughly 59.52. Therefore, we can finally find the initial temperature by putting all the information that we have found into the general equation when the time is 0. Finally, we can find the initial temperature from this problem, which is about 64.52 Fahrenheit. The next problem is about mixture problem. Suppose in a tank with capacity V there is a V0 liter of solution with A0 amount of salt. At time equals to 0, at the rate of x liter per second, a salt solution with concentration of C in gram liter poured into the tank, and after completely mixed with the solution in the tank, sound goes out at the rate of R out with the concentration of C out, which is A over initial volume plus, in parentheses, rate in minus rate out times T. So dA dt equals to AB minus C times AT over V plus A minus CT. That is the general equation. So for the first example, we have a tank which has 100 gallons of salt. The rate at which salt is going in is 6 gallons per minute, and the concentration is half a pound per gallon. And the rate at which water is going out is 4 gallons per minute. So the concentration in the beginning is 10 pounds. And we were asked to find the amount of salt when the time is 30 minutes. First, we put in the formula, which is differential of A in respect to T equals to rate in times concentration in minus rate out times concentration out. So that is A times B minus C AT over V plus A minus C T. So we put in the values that we get from the problem. Once we simplify the equation, we will then rearrange the equation into a linear equation, and from then on we will solve it like a normal linear equation. After getting the equation of A of t, we'll then take when time equals to 0, which is when the concentration of the salt in the tank is equals to 10 pounds. So we'll equate them together, and then we'll just solve for the problem to get the C. Once we have acquired our C, we just simply put into the equation and we will have our general solution. So we just simply plug in when time equals to 30 and substitute t for 30 and we'll get our answer, which is 64.375 pounds. Last but not least, we have the RC circuit problem. And in the first example, we have a circuit which has a resistor, a voltage source, and a capacitor. The voltage of the voltage source is 200 volt and the resistor has 1000 ohm and the capacitor has 5 times 10 to the power negative 6 current. So the general equation that we will have is 200 equals to IR plus Q over C. Then we plug in all the information that we have and simplify it. We will get a linear equation and solve it normally. Given that when time equals to 0, the current is 0.4 ampere, at t equals to 0, dq over dt equals to 0.4. So we just plug it in our general solution. And we will get what Q is. By plugging in what Q is, we are then able to find out what C is. In this question, C equals to 1 over 500. So we are able to find out what Q is. The next application problem we will have is the RL circuit problem. In this problem, we will have the inductor, voltage source, and the resistor in this circuit. The resistor has 1 ohm and V equals to sine T and L equals to 1 H. So we have the general equation. Sine T equals to 1I minus 1 dI over dt. When we simplify, we will just get a linear equation and we will just solve it as a linear equation, which is rather simple. We then rearrange the equation to get I, and that is our final answer.